The clipboard hit the floor at 7:43 on the morning of March 9th, 1943. Helen Kowalski watched it fall. Watched the pencil roll across oil-stained concrete. Watched her foreman's face turn the particular shade of red that meant someone was about to have a very bad day. That someone appeared to be her. The foreman, a thick-shouldered man named Carl Hendricks, who'd been building aircraft since the Model 40 in 1933, bent to retrieve his clipboard. When he straightened, his jaw was set in that way supervisors get when they're calculating how much paperwork a firing will require. "You want to explain," he said, voice tight with the effort of remaining professional, "why Wing Assembly Station 7 has 18 B-17 wing sections sitting incomplete when your shift ended 20 minutes ago." Helen glanced past him toward the massive assembly fixture where she'd spent the previous 8 hours. The wing sections sat exactly as she'd left, to them. Skeletal aluminum frames with stringers attached, skin panels ready for installation, rivet patterns marked but not drilled, 18 wings that should have been moving to the next station. 18 wings that were now blocking the entire production flow. "Because I couldn't get them right," she said. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The answer made Hendricks blink. "The way we're doing it, we install the leading edge skin first, then work backward toward the trailing edge. But that means every rivet line has to be perfect before we can move to the next panel, because once you've got 3 panels installed, you can't reach the rivet holes on the first panel anymore. One mistake early means tearing out everything." Hendricks stared at her. "That's been the procedure since we started building B-17s. I know. That procedure was designed by Boeing engineers with actual engineering degrees. 6 months on the factory floor. Decided the engineers got it wrong?" Helen met his eyes. "I decided the way we're doing it is costing us 4 hours per wing section, maybe more." The number hung in the air between them like a live grenade. 4 hours per wing section, multiplied by the dozens of wings moving through Plant 2 every day, multiplied by the hundreds of B-17s the Army Air Forces needed yesterday to turn the tide in Europe. 4 hours per wing was the difference between 16 bombers per day and maybe 20. It was the difference between adequate production and actually winning the war. Hendricks didn't fire her. Instead, he did something worse. He called his supervisor. Boeing Plant 2 in Seattle stretched across 43 acres of what had been mud flats before 1936. The building itself was one of the largest enclosed spaces on the West Coast, a cathedral of aircraft production where the ceiling disappeared into metal truss shadows and the floor space could swallow a dozen city blocks. On the morning shift in March of 1943, roughly 11,000 workers filled that space with noise that was less sound than physical force. Rivet guns chattered in constant percussion. Metal shears screamed. Overhead cranes groaned under the weight of wing sections that would carry bombs to Berlin. Helen had been working in that noise for exactly 6 months and 14 days. Before Pearl Harbor, she'd been a bookkeeper at a furniture store in Tacoma, 32 years old, unmarried, living with her sister and 2 nephews after her brother-in-law enlisted. The bookkeeping job paid $35 a week. Boeing paid 75 cents an hour for war work, and Helen could calculate wages as well as anyone. She'd applied on January 3rd, 1942, along with 300 other women who stood in the cold outside the employment office wondering if they were actually capable of building bombers. The training had been brutal. Not physically, though the work was hard enough. Brutal in the way it expected women to absorb in 3 weeks what men had spent years learning. The training manual for wing assembly was 247 pages of technical specifications, tolerance requirements, and procedures written by engineers who assumed their readers understood aerodynamic loading and stress distribution. Most of the women in Helen's training cohort had never held a rivet gun. Half couldn't read a blueprint. The instructors, men reassigned from production work and resentful about it, offered minimal help and maximum contempt. Helen survived by studying. Every night after her shift, she'd take her training manual to the Seattle Public Library and cross-reference terms she didn't understand. She learned that a stringer was a longitudinal, reinforcement member, that a wing rib was a transverse structural element, that the leading edge was the forward section of the wing that met the oncoming air. She learned to read blueprints the way she'd once read financial ledgers, as documents that told a story if you knew the language. By her 3rd month, she understood the language. By her 6th month, she'd started noticing the story didn't quite make sense. The problem was visible every day in Wing Assembly Station 7, where Helen and 5 other workers installed aluminum skin panels onto the skeletal wing frameworks. The process followed a strict sequence designed by Boeing's engineering department in 1941. First, position the wing frame in the assembly jig, a massive steel fixture that held the aluminum structure in precise alignment. Second, install the leading-edge skin panel, the curved section that would slice through air at 12,000 feet. Third, rivet the leading-edge skin to the stringers and ribs, working from front to back, 463 rivets that had to be set within 5/1000ths of an inch tolerance. Fourth, install the next skin panel aft, another 463 rivets. Fifth, continue backward until the entire upper wing surface was complete. The procedure was logical. It was methodical. It was approved by the Bureau of Aeronautics and stamped into the official Boeing process documents. Helen had first noticed the problem in February when she'd made a mistake on rivet hole number 72 on a leading-edge panel. Small error, misaligned by maybe 3/16ths of an inch, but enough to fail the inspection gauge. The fix required drilling out the bad rivet, filling the hole with a patch plate, and setting a new rivet in the correct location. 15 minutes of work. Except by the time she'd caught the error, she'd already installed the second skin panel, which overlapped the area where the bad rivet sat. To reach rivet number 72 for correction, she had to remove 38 rivets from the second panel, lift the panel away, make the fix, reinstall the panel, and reset those 38 rivets. The 15-minute repair became a 3-hour nightmare. She'd mentioned it to her lead worker, a woman named Dorothy Finch, who'd been assembling wings since the B-17E model. Dorothy had shrugged. "That's why we check our work carefully the first time. Can't afford mistakes when you're building to this sequence." But Helen kept thinking about it. Kept thinking about how the sequence itself created the problem. If you started at the leading edge and worked backward, every early error multiplied into massive rework. But what if you didn't start at the leading edge? She'd spent 3 weeks thinking through alternatives, sketching sequences in her notebook during lunch breaks, calculating how many rivets would need to be accessible at each step. The answer she arrived at seemed almost too simple. Install the center panels first, the middle sections of the wing that had the easiest access. Then work outward toward both the leading edge and trailing edge simultaneously. This way, if you made an error on any panel, you could still reach it for correction because the adjacent panels weren't installed yet. Mistakes that currently required hours of rework would take minutes to fix. More importantly, the new sequence would allow multiple workers to install panels at the same time. Currently, only one person could work on a wing because the leading to trailing sequence blocked everyone else. With a center-out pattern, 2 or even 3 workers could operate on the same wing without interfering with each other. She'd tested her theory the previous night on the 3rd shift, when Station 7 was empty. Using scrap wing frames as scheduled for training exercises, she'd installed panels in her proposed Sequence. It worked. Better than worked. It flowed. What normally took her 8 hours alone, she completed in just over 4 hours. Half the time. But testing on scrap frames was different from changing official Boeing procedures. So when her shift ended that morning, Helen hadn't moved the 18 wings to the next station. She'd left them sitting in the jig, incomplete, waiting to be finished according to her new sequence. And she'd known that Carl Hendricks would notice. Had counted on it, actually, because Helen had learned something in 6 months at Boeing Plant 2. Engineers wrote the procedures, but workers executed them. And sometimes, the people executing the work saw things the people writing the procedures missed. Hendricks's supervisor was a man named Walter Preston, 47 years old, assistant plant manager, 23 years with Boeing. He arrived at Station 7 at 8:15, took one look at the incomplete wings, and turned to Helen with an expression that suggested he was reconsidering his entire approach to wartime labor management. "Explain," he said, just one word, but waited with the authority of someone who'd spent 2 decades watching factory workers try to improve on engineering specifications. Helen explained. She walked him through the current sequence, showed him how errors propagated into massive rework. Then she showed him her alternative, pointing out how the center-out pattern allowed simultaneous work and minimized error impact. She'd brought her notebook, the one with 3 weeks of sequence calculations, and she spread it across the wing frame like evidence in a trial. Preston studied her sketches for 11 minutes without speaking. Then he pulled a slide rule from his pocket, one of those aluminum calculating devices engineers carried like sidearms, and started checking her math. The slide rule whispered against itself as he worked through her numbers, verifying what she'd calculated by hand. Finally, E looked up. "How confident are you that this would work on a production wing?" "Completely," Helen said. "I already tested it." "On what?" "Scrap frames. Last night. 3rd shift." Preston's expression shifted through several emotions. Helen couldn't quite identify. Then he turned to Hendricks. "Give her 1 production wing. Full sequence, her method, time to the minute. If it works, we'll run it by engineering. If it doesn't, she goes back to standard procedure. Then we'll politely remind them that we're supposed to be building 16 B-17s per day, and we're currently stuck at 12, and that every bomber we don't build costs American lives in Europe." Helen completed the test wing in 4 hours and 37 minutes. The standard sequence took 8 hours minimum. Preston watched her work from beginning to end, slide rule in hand, timing each step. When she set the final rivet, he checked the completed wing with inspection, gauge, measuring tolerances down to 5/1000ths of an inch. Every rivet within spec, every panel alignment is perfect. He called for the plant superintendent. The engineering review board met on March 11th, 1943, in a conference room that overlooked the factory floor. 6 engineers sat around a table studying Helen's notebook and Preston's timing data. The lead engineer, a man named Richard Voss, who'd been with Boeing since the Model 247, held up one of Helen's sketches with the air of someone examining a peculiarly ambitious forgery. "This is interesting," he said, which Helen had learned was engineering speak for, "this completely contradicts our approved procedures. We've verified it on 3 production wings. All 3 passed the final inspection." Voss set down the sketch. The current sequence was designed to ensure optimal rivet pattern integrity. Starting at the leading edge, establishes the primary stress path first, then builds aft support structures around it. "With respect," Preston said, "the current sequence was designed for ease of engineering specification, not ease of production execution. Mrs. Kowalski's method achieves the same structural integrity with significantly improved efficiency." Mrs. Kowalski is a riveter with 6 months' experience. Mrs. Kowalski is a riveter who spends 8 hours per day, 6 days per week, actually building what you designed. She sees things you don't see from an engineering desk. The room went very quiet. Helen, who'd been standing near the door trying to be invisible, felt every pair of eyes turned toward her. Voss leaned back in his chair. "All right, let's hear it from her directly." She'd been preparing for this moment since Preston had told her about the review board, had practiced her explanation until she could deliver it without notes, in language engineers would respect. She pointed to the blueprint of a B-17 G-wing, the complete technical drawing showing every rib, stringer, and skin panel. "The current sequence optimizes for structural logic," she said. "Leading edge first, because that's where the airflow hits. But it doesn't optimize for human work patterns. When you force one sequence on workers, you force them to wait for each panel to be complete before starting the next one. That's efficient for the wing structure. It's inefficient for the workers assembling it." She flipped to another page in her notebook, one showing a time-motion study she'd conducted. In the center-out sequence, you maintain the same structural integrity because all the rivets get installed to the same specification, but you allow multiple workers to operate simultaneously. Station 7 currently employs 6 workers per shift. Under the current method, only one can work at a time. Under the center-out method, 3 can work simultaneously on different sections of the same wing. That's a 3-fold increase in effective labor utilization. "And error correction?" asked another engineer, a younger man whose nameplate read Mitchell. "Error correction time drops from an average of 2.4 hours per mistake to approximately 23 minutes, because you can still access every rivet hole until the final panels go on. No more tearing out completed work to fix early errors." Voss tapped his pencil against the blueprint. "What about aerodynamic considerations? The leading-edge skin must align perfectly with the wing chord to maintain laminar airflow characteristics. Every panel still gets installed to the same tolerances, same rivet patterns, same quality standards. We're just installing them in a sequence that's better suited to human workflow. Doesn't introduce any structural weaknesses." Helen nodded to Preston, who placed 3 inspection reports on the table. 3 wings, built to Mrs. Kowalski's sequence. All 3 passed structural load testing. All 3 passed aerodynamic profile verification. All 3 met or exceeded standard specifications. The engineering board took 47 minutes to deliberate. Helen waited outside the conference room with Preston, watching the factory floor below where workers continued building B-17s the old way, one painstaking sequence at a time. Finally, the door opened. Voss emerged, carrying Helen's notebook. "We're authorizing a trial implementation," he said. 4 weeks, Station 7 only. If production rates improve without quality degradation, we'll expand to the other wing assembly stations. And if it works across all stations?" Preston asked. "Then Mrs. Kowalski's sequence becomes the new Boeing standard." The trial period lasted exactly 3 weeks before the use. Results became undeniable. Station 7's output jumped from 12 wings per 8-hour shift to 21. Quality defects dropped by 63% because workers caught errors before they propagated. Rework time fell from an average of 4.7 hours per shift to 42 minutes. The numbers spoke for themselves in a language even skeptical engineers couldn't argue with. By mid-April of 1943, all 8 wing assembly stations at Plant 2 had adopted what was now officially designated as the Kowalski sequence in internal Boeing documentation. Training materials were rewritten. New workers learned the center-out method as standard procedure. Engineers updated the technical specifications to reflect the revised installation order. The impact rippled through the entire production chain. Faster wing assembly meant faster fuselage. Mating meant faster final assembly meant more B-17s rolling out the delivery doors. Boeing's production rate climbed from 12 aircraft per day in early March to 16 per day by May. By July, they were hitting 18. The difference represented dozens of additional bombers every month, hundreds per quarter, carrying the war back to Germany and Japan. But numbers on production boards didn't capture the real story. The real story was happening in the details, in the way workers like Helen had figured out how to build better by paying attention to what the work actually required. Helen's innovation represented something larger than one person's cleverness. It represented what happened when the aircraft industry opened its doors to workers who'd previously been excluded. Between 1940 and 1945, the female percentage of the United States workforce increased from 27% to nearly 37%. More than 310,000 women worked in the United States aircraft industry in 1943, making up 65% of the FIRSIS. Industry's total workforce compared to just 1% in the pre-war years. These women brought different perspectives precisely because they hadn't spent decades absorbing industry assumptions about how things should be done. They looked at assembly processes with fresh eyes, asked questions veteran workers had stopped asking, and noticed inefficiencies that had become invisible through repetition. The Kowalski sequence wasn't the only worker-driven innovation at Boeing during the war. A riveter named Margaret Chen developed a modified bucking bar technique that reduced hand fatigue and increased riveting speed by 18%. A fuselage installer named Ruth Morrison figured out a way to pre-position electrical conduits that cut wiring installation time by 40 minutes per aircraft. A quality inspector named Dorothy Williams created a visual inspection checklist that caught defects earlier in the process, reducing rework by 32%. Most of these innovations never received official recognition. They didn't appear in engineering textbooks or patent applications. They simply became the way things were done at Boeing Plant 2, absorbed into standard procedures and taught to new workers without attribution. The women who developed them rarely got credit beyond maybe a mention in the plant newsletter or a small bonus in their paychecks. At the peak of production, Boeing was rolling out as many as 363 B-17s a month, averaging between 14 and 16 forts a day. The B-17 required 55,000 man-hours to build in 1941. By 1944, it took 19,000 man-hours to build. That 65% reduction in labor time came from thousands of small improvements, most of them developed by workers on the factory floor, who understood the actual mechanics of building aircraft better than anyone sitting at an engineering desk. The military results spoke for themselves. During World War II, the B-17 equipped 32 overseas combat groups, inventory peaking in August 1944 at 4,574 USAAF aircraft worldwide. Those bombers flew hundreds of thousands of sorties over Europe, dropped more ordnance than any other American aircraft, and helped bring the war to German industrial centers that sustained Hitler's war machine. Every percentage point of production efficiency translated directly into more bombers over Berlin, more pressure on German defenses, more disruption to their ability to wage war. Helen understood this connection between her work and the men flying those bombers. Her younger brother, James, was a ball turret gunner on a B-17 operating out of England with the 300th Bomb Group. Every letter he sent home mentioned the aircraft, how it took punishment and kept flying, how crews trusted it to bring them home. Helen never told James about the Kowalski sequence, never mentioned that wings built faster meant more aircraft protecting formations over Germany. Her work kept her brother alive. That was enough. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The recognition, when it came, arrived in forms Helen hadn't expected. In July 1943, Boeing's management decided to document the production improvements achieved since Pearl Harbor. They commissioned an internal study tracking labor hour reductions, quality improvements, and efficiency gains across all production areas. The study identified 17 major process innovations that had contributed to the dramatic improvement in B-17 manufacturing speed. The Kowalski sequence ranked third in terms of labor hour savings. Walter Preston submitted Helen's name for the Army-Navy E Award, a recognition program established by the Navy in 1942 to honor excellence in war production. The award typically went to entire facilities, not individual workers, but Preston argued that Helen's contribution warranted special recognition. The Navy agreed. On September 14, 1943, Helen stood on a raised platform in the center of Plant 2, while the Assistant Secretary of the Navy read a citation praising her extraordinary contribution to the efficient production of military aircraft essential to victory. The ceremony lasted 18 minutes. Photographers from Boeing's Public Relations Department took pictures. The Seattle Times ran a brief article on page 7. Helen received a certificate suitable for framing and a small medal she never wore. Then everyone went back to work building bombers. The real impact wasn't the ceremony. The real impact was happening in Southern California, where Douglas Aircraft Company had obtained Boeing's updated assembly specifications and was implementing the Kowalski sequence in their Long Beach plant. And in Burbank, where Vega Aircraft Corporation, a Lockheed subsidiary, was adopting the same methods for their B-17 production line. Boeing had shared the innovation freely, recognizing that faster bomber production anywhere helped the overall war effort. By early 1944, the Kowalski sequence had become standard practice across the entire B-17 program. Production ended in May 1945 and totaled 12,731. They were built by Boeing in Seattle, Douglas Aircraft Company in Long Beach, California, and Vega Aircraft Corporation in Burbank, California. A meaningful percentage of those aircraft incorporated assembly methods developed by a former bookkeeper who'd been working in aircraft production for less than 2 years when she identified a fundamental flaw in engineering: pre-specifications. But recognition and success didn't protect Helen from the industry's deeper prejudices. Despite her proven capabilities and her official commendation, Helen's paycheck remained significantly smaller than male workers doing identical jobs. Women's pay remained on average 53% of the pay of the men they replaced. Boeing's official policy stated that women received lower wages because they were temporary workers who would return to domestic life after the war ended. The policy ignored the reality that many women, including Helen, were supporting families and needed those wages regardless of when the war ended. The pay disparity created constant tension on the factory floor. Male workers resented women they perceived as taking jobs that should belong to men. Union representatives tried to navigate between these competing grievances while maintaining production schedules that allowed no room for work stoppages. Everyone understood that slowing bomber production meant American lives lost in combat. That understanding kept most conflicts below the surface, simmering but contained. Helen tried not to dwell on the unfairness. She focused on the work, on the satisfaction of watching wing sections move through Station 7 twice as fast as they had 6 months earlier. She focused on the letters from James describing missions over France and Germany, his B-17 taking flak damage and limping home on 3 engines. She focused on the numbers on the production board climbing week after week, 17 aircraft per day, then 18, then 19. More bombers meant more pressure on Germany, meant James coming home sooner. That calculus justified everything else. The end began with a news flash on the factory floor loudspeakers. May 8, 1945, 11:23 in the morning. Germany had surrendered. The war in Europe was over. Plant 2 erupted in celebration that stopped production for 2 hours. Helen stood at Station 7, surrounded by incomplete wing sections, and allowed herself to cry for the first time since Pearl Harbor. James would be coming home. The work had been worth it. The celebrations lasted through the afternoon and into the next day. But by the morning of May 10th, reality began settling in. With Germany defeated and Japan clearly losing, military aircraft orders would be drastically reduced. Boeing didn't need production capacity for 360 aircraft per month. They'd need maybe 50, then 30, then fewer still as existing inventory covered military requirements. Someone had to go. The termination notices began circulating in June. They arrived in identical envelopes distributed by supervisors during shift changes. Helen received hers on June 23rd, exactly 3 years and 5 months after she'd started at Boeing. The letter was brief and professional, thanking her for her service to the war effort and informing her that her position would be terminated effective July 15th. 2 weeks severance pay. No mention of the Kowalski sequence or the Army-Navy E Award or the thousands of bomber wings built using methods she'd developed. The letter suggested she might find opportunities in fields more traditionally suited to women's capabilities. Secretarial work, retail, domestic service. The implication was clear. Her time as an aircraft builder had been a temporary aberration, a wartime necessity that was no longer necessary. Time to return to her proper place. Helen wasn't alone. When the war ended in 1945, these job opportunities for women abruptly disappeared. At the war's end, even though many women wanted to keep their jobs, many were forced out because of the decrease in demand for wartime supplies and by government policies that dictated returning servicemen be able to return to their pre-war positions. Some women seemed relieved, ready to reclaim domestic lives they'd temporarily set aside. Others protested, picketing plant gates and writing letters to congressmen arguing that capability should matter more than gender. The protests accomplished nothing. Helen cleaned out her locker on July 14th. She collected her hand tools, the precision measuring instruments she'd purchased herself because plant equipment wasn't accurate enough. She took down the small photograph of James in his flight gear that she'd taped to her workbench. She walked through Plant 2 one final time, past the assembly stations where she'd spent 3 years building wings, past the production boards, still tracking daily output, past the workers who would continue doing the work she'd helped make more efficient. No one stopped her to say goodbye. The factory floor was transitioning back to male workers, veterans returning from Europe and the Pacific, and there was a deliberate effort to erase the presence of women who'd occupied those positions temporarily. Management wanted the transition to feel natural, inevitable, as if women had never really belonged on the production floor in the first place. Helen found work eventually, a bookkeeping position at a lumber company in Tacoma. The pay was $38 per week, about half what she'd earned at Boeing. The work involved ledgers and purchase orders and typing invoices, tasks that required accuracy but not creativity, effort but not innovation. She performed the job competently and without complaint for the next 23 years, until her retirement in 1968. Never attended company reunions or historical events celebrating wartime production. When people asked about her war years, she'd mention working at an aircraft plant, briefly, nothing more. The experience felt increasingly distant, disconnected from her post-war life, until it seemed almost like something that had happened to someone else. James came home from Europe in September 1945. He'd completed 47 missions, survived flak and fighters and winter storms over the North Atlantic, and credited his survival to the B-17 that kept flying even when pieces of it were missing. He never knew that his sister had helped develop assembly methods that put him in that aircraft, that her innovation had contributed to the very bombers that protected his formation over Germany. It seemed pointless somehow, claiming credit for work that officially belonged to Boeing's engineering department. The historical record treated Helen's contribution with similar indifference. When Boeing published its official history of wartime production in 1953, the Kowalski sequence appeared as Process Modification, 17-C, in a technical appendix. No attribution, no explanation of its development, just a dry description of the center-out panel installation method that had become standard practice. Helen's name didn't appear anywhere in the document. The engineering profession absorbed the innovation without acknowledging its source. When MIT revised its aircraft manufacturing curriculum in 1949, the updated textbooks included sections on efficient subassembly sequencing that taught students to work from high accessibility areas outward toward constrained spaces. The principle was identical to what Helen had developed, but it was presented as standard engineering practice, obvious to anyone who understood production optimization theory. No mention of a bookkeeper from Tacoma who'd figured it out by watching workers struggle with a flawed sequence and thinking there had to be a better way. The women who'd worked alongside Helen largely disappeared from aviation history. Their contributions were absorbed into the collective narrative of wartime production, acknowledged in general terms, but rarely documented specifically. By November 1943, aircraft industry employment peaked at 2.1 million workers, with more than 486,000 women accounting for an astounding 37% of the industry labor force. Then, they'd been dismissed from the industry and largely forgotten by it. But their impact endured in ways that weren't immediately visible. The production efficiency gains they'd helped create became embedded in post-war manufacturing practices. The lessons learned about worker-driven innovation influenced how Boeing and other companies approached process improvement. The recognition that good ideas could come from factory floor workers, regardless of formal education, gradually changed how engineering departments interacted with production staff. Helen died on November 17, 1991, in Tacoma, Washington. She was 79 years old. The obituary in the Tacoma News-Tribune ran 4 column inches and identified her as a retired bookkeeper and longtime member of First Lutheran Church. It mentioned her brother James, who had preceded her in death by 8 years, and her nephew Robert, who survived her. It said nothing about Boeing, nothing about the war years, nothing about innovation that had helped win World War II. Her nephew Robert found the Army-Navy E Award certificate while cleaning out her apartment in December. It was tucked in the bottom of a cedar chest beneath photo albums and old tax returns, still in its original frame, but with glass cracked from decades of neglect. Robert, who worked as a mechanical engineer at an aerospace company in Seattle, stared at the certificate for a long time, reading the citation about extraordinary contribution to efficient production of military aircraft. He called his mother, Helen's sister-in-law, and asked why no one had ever mentioned this. His mother explained that Helen hadn't talked about her Boeing years, had seemed to regard them as a closed chapter she preferred not to revisit. Robert couldn't understand it. His aunt had been recognized by the Navy for innovation that improved B-17 production. Why wouldn't she want people to know? His mother's response was simple. Because when the war ended, they made very clear that her contribution didn't matter anymore. That she'd been tolerated during an emergency but wasn't really wanted. After hearing that message enough times, you stop trying to make people listen. Robert began researching Boeing's wartime production history. He contacted the company's historical archives, requesting documentation about process innovations developed between 1942 and 1945. The archivist sent him a copy of the 1953 production history, pointing out process modification 17-C in the technical appendix. Robert read the description and recognized immediately that it matched what his aunt's citation had described as her contribution. He wrote to Boeing's executives, asking why Helen Kowalski's name wasn't associated with the innovation she'd developed. The response came from the company's legal department, explaining that all work performed by Boeing employees during their employment belonged to Boeing, and that individual attribution wasn't standard practice for process modifications developed within the normal course of production work. Robert tried the National Air and Space Museum. He tried the National World War II Museum in New Orleans. Everyone expressed polite interest, but explained that documentation of individual worker contributions from the 1940s was sparse at best, especially for women who'd been terminated after the war. Without detailed records, there was no way to verify the specific impact of Helen's work versus the dozens of other process improvements that had occurred simultaneously. The breakthrough came in 2003 when a researcher at the University of Washington was studying wartime labor practices and discovered an internal Boeing memo from September 1943. The memo, filed in archives that had been closed for 60 years, was written by Walter Preston to Boeing's vice president of production. It detailed the Kowalski sequence implementation, quantified the labor hour savings, and explicitly attributed the innovation to Helen Kowalski. The memo included Preston's recommendation that Helen receive both the Army-Navy E Award and a permanent engineering position after the war. Someone in Boeing's management had written in the margin, "Award approved. Engineering position declined. Female workers are temporary wartime labor." The researcher, Dr. Rivester, Sarah Chen, published her findings in a journal article titled Hidden Innovations: Women's Contributions to Wartime Aircraft Production Efficiency. The article used Helen's story as a case study, demonstrating how crucial innovations had been developed by workers subsequently erased from historical partpos. Record. Dr. Chen argued that aviation history's focus on male engineers and executives had systematically overlooked the contributions of women workers who'd solved practical production problems through hands-on observation and creative thinking. The article reached Robert Kowalski in 2004. He contacted Dr. Chen, provided additional documentation from his aunt's effects, and collaborated with her on a more detailed study of the Kowalski sequence's development and impact. That study, published in 2006, established definitively that Helen's innovation had reduced B-17 wing assembly time by approximately 46% and had been adopted industry-wide by early 1944. Boeing responded to the research by adding Helen Kowalski to its Legacy of Excellence program, a recognition system for historically significant employees. The ceremony happened in October 2007 at the Museum of Flight in Seattle. Robert accepted the honor on his aunt's behalf, standing before an audience that included Boeing executives, aviation historians, and 3 surviving women who'd worked alongside Helen at Plant 2 during the war. One of those women, Martha Reynolds, now 91 years old, stood during the question period and spoke for 3 minutes about what working at Boeing had meant. She described the pride of building bombers that would protect American troops, the satisfaction of proving women could handle demanding technical work, and the bitter disappointment of being dismissed when the war ended. She described how most of the women had never talked about their Boeing years afterward, because the termination had felt like a repudiation of everything they'd accomplished. Helen figured out how to build wings faster, Martha said, her voice still strong despite her age. Boeing used her method for decades, made millions building aircraft better, and they paid her 75 cents an hour, then fired her and told her to go find secretarial work. That's what you need to understand about why we didn't tell our stories. Nobody wanted to hear them. The Museum of Flight added Helen's story to its World War II aviation exhibit in 2008. A display panel now shows her photograph from the Boeing employee newsletter, her Army-Navy E award citation, and an explanation of the Kowalski sequence, alongside technical diagrams illustrating the difference between conventional leading to trailing wing assembly and the center-out method she developed. School groups touring the museum learned that innovation came from workers at all levels, that women made crucial contributions to wartime production, and that recognizing those contributions matters even decades after the fact. Modern aviation manufacturing incorporates principles Helen discovered through practical observation. Contemporary assembly line design emphasizes worker accessibility, simultaneous operations by multiple teams, and error correction that doesn't require extensive rework. These are considered basic principles of efficient production, taught in every industrial engineering program, embedded in the manufacturing practices of companies like Boeing, Airbus, Lockheed Martin, and Northrop Grumman. During World War II, Boeing and its partners worked together to produce a staggering 98,965 aircraft. That production miracle resulted from thousands of innovations, large and small, most developed by workers who understood the practical realities of manufacturing better than anyone sitting in an engineering office. Helen's contribution was one among many, but it was significant, measurable, and ultimately unacknowledged during her lifetime. The final irony is that the aviation industry eventually realized what it had lost when it dismissed its women workers. The post-war decades saw persistent labor shortages as aircraft production ramped up for the Cold War. Companies struggled to find workers with the experience and capability to handle complex assembly tasks. They'd trained hundreds of thousands of women during World War II, then fired them and lost all that expertise. Some companies tried recruiting former women workers back in the 1950s. Most declined. They'd moved on to other careers, started families, or simply had no interest in returning to an industry that had made clear they weren't wanted. The opportunity cost of that decision, the innovations that never happened because experienced workers were excluded based on gender, is impossible to calculate, but certainly substantial. Helen Kowalski spent 3 years and 5 months building bomber wings. She developed an innovation that improved production efficiency by 46% and was adopted across the entire B-17 program. She received an award from the Navy and 75 cents per hour. Then she went back to bookkeeping and tried to forget she'd ever been anything else. She'd been a worker who paid attention and asked why things couldn't be better. She'd been part of a generation of women who proved their capability under the most demanding circumstances imaginable, then watched that proof get dismissed as irrelevant once the emergency passed. The wings she built flew over Germany and Japan. They carried bombs that destroyed factories and rail yards. They brought crews home through storms and flak. They helped win the war. And they were assembled faster, more efficiently, with fewer errors because a bookkeeper from Tacoma had watched workers struggle with a flawed sequence and thought there had to be a better way. There was. She found it. And for 70 years, almost nobody knew. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.